Good afternoon, all. To the continuation of the confirmation analysis, right? So today we are going to discuss about the confirmation of cyclohexanone, right? So generally, in the previous classes, we discussed about the confirmation of that cyclic, right? The cyclic aliphatic, right? Aliphatic cyclic compounds here. Means alicyclic compounds like cyclopentane, cyclobutane, cyclohexanes, and now it is the confirmation of cyclohexanone ketone here, right? So generally the ketone, okay, the cyclohexanone, where it is also you can study the confirmation of cyclohexanone, uh, right? So by doing that some confirmation changes here. Right? So because the presence of the carbonyl group here, right? The presence of carbonyl group, so it will be effect on the reactivity actually, right? The reactivity. So generally the carbonyl compounds they undergo the addition reactions, right? The carbonyl compounds undergo the addition reactions. So when you do the addition with the sodium, what is that? HCl, okay, hydrogen cyanide, or the reduction reaction with the sodium borohydride or the lithium aluminum hydride here. So that the conformation will be effects on all these reactions like addition reactions, reduction reactions here. Okay, and right. So here generally when you see that addition reaction, the addition of HCl, right? The addition of HCl, it is 70 times faster than the what is that di-N octyl ketone here, right? And here it is 355 times faster than the di-N hexyl ketone, means a reduction. So that is due to the conformation here. Okay, so the orientation of the group also plays important role here. You see here in this particular cyclohexanone. Right? So here the bond angle between the here in the cyclohexanone, you see here the bond angle where this is 116 here, and here is a 122, right? The carbon and the oxygen here, right? Carbon and CO. So this bond angle is a 122, right? 122 here, and carbon and carbon bond angle is a 116 here, right? So actual the actual bond angle is a right. So carbon for carbon it is 109, but it is carbon it is how much it is 116. So it is 7, right? So it is nearly 7 approximate, right? 7 degrees deviation is there. So very slight deviation, right? The very little deviation, but the CO, okay, the carbon and C double bond word, this is 122. So how much it is? 109 minus 122. It is more deviation is there. You can see, right? How much it is? There are 23 degrees deviation is there. That's why, right? So it suffers from the angle strain, right? It suffers from the angle strain here. So in the planar structure, you can see in the planar structure that deviation, this much angle deviation is there, and it suffers from the angle strain here. That's why if you convert that, right, planar structure into the puckered structure, okay, another conformation. So then the angle strain will be reduced here. So some relief will be obtained from this angle strain here, right? So for that, we will convert this particular conformation, right? The planar conformation into that puckered chair conformation, chair and boat conformation, chair and half chair and boat conformation, twist boat conformation here, right? And among these all conformations, so which conformation is stable? So in general, right? So in general, the chair conformation is for the cyclohexane, right? For the cyclohexane, here the chair conformation of cyclohexane is stable here, right? The conformation of cyclohexane is stable, but uh, in case of carbonyl group here, right? In case of cyclohexanone, okay, so where the cyclohexanone, right? So it more populated, right? It is more populated in the twist boat here, right? Twist boat conformation, because the orientation of carbonyl group is, right? The orientation of carbonyl group is, it is away from the groups here or the atoms here, right? That's why it is more stable. Okay, so in the chair conformation, you see, right? In the chair conformation, so here this carbonyl group, right? So there is a hydrogen here, right? So it suffers from the some steric strain here. Here also you see, right? So either it is what is it, upwards or the downwards, whatever, but it suffers from this steric strain here. That's why if you convert this into the another conformation, right, twist boat conformation, the boat conformation also it suffers some. Okay, in the boat conformation also you can see that steric strain here. So, but in this particular twist boat, right? So where it is away, right? So this carbonyl is away from the, it is away from this right, the ring here. It's away from the ring, or you can see that the groups are whatever the bonds, right? Here this, because this bond is above the plane here, and it is on the plane, right? So this CO carbonyl is on the plane here, on the plane, and it is above the plane here. That's why no steric repulsion or the steric strain is faced encountered by your carbonyl group here. That's why that this conformation, right? So the twist boat is more stable, and here in this conformation also you can see when this carbonyl group is, right, so nearer to this bond here, carbon carbon single bond, right? So it is somewhat facing some steric repulsion, so it is less stable here. Okay, but here you see this is away. Okay, this bond is, this is above the plane, and this is CO group is away here, but here you see this is the, okay, here some hydrogens are there, right? That's why it's face some steric repulsion. So you this is a less stable conformation, and this is a more stable conformation here. And very very important here, the two alkyl ketone effect, right? It's very very important. Two alkyl ketone effects, three alkyl ketone effects. These are important topics here. Two alkyl ketone effects. So in the unsubstituted cyclohexanone, right? For the non-substituted, non-other, right? The normal cyclohexanone or the non-substituted cyclohexanone. So generally, there is no differentiation here. Okay, because there is no bulky groups or any substitutions are there. That's why generally we can predict, right? You can predict the stability of these particular conformations here. But in the substitution is there. That substitution is at second position. That is two alkyl ketone effect. So in that case, okay. So the what is the effect of the ketone group on the C2 substitution here? This is C1, here the C2, C3, C4, C5, like that, C6 here. Okay. So here the second substitution, when it is in the equatorial direction or when it is in the axial direction. So what will be the effect of this ketone group here on the that substitution? Okay, so means how it will be affects for the reactions, carbonyl group reactions like addition reactions and reduction reactions here. Okay, so how it will be impact on that one. So you can see. So generally here, okay, so when the bulky groups is substituted at C2 position here, so generally it will be destabilized, right? It will be destabilizes that particular equatorial conformation, right? Here you see this is the equatorial conformation. So when the equatorial at equatorial position, if any bulky groups R group here, R group is there, so generally this carbonyl group will be destabilized at, right? The carbonyl group will be destabilized because this bulky group is towards that carbonyl group. Okay, so it is towards that carbonyl group here. That's why it will face some steric repulsion. Okay, and here you see that some what is that Gaussian interactions also there. If you convert it into that particular Newman projection, so you will see some uh, okay one Gaussian interaction here. So that is also one of the factors, destabilizing factor here, right? So it results the substitution of the bulky group adjacent to that carbonyl group. It results in the destabilizing of the conformation here, right? Okay. And you see the effect of various means substitution of various groups here. You see in the cyclohexanone, right here the methyl. So the right the impact of that methyl substitution is right. So here it is 6.6 here. Hmm. And in the cyclohexane, in the normal cyclohexane, the impact this one. Okay, here. So the energy, right? The energy, the conformation free energy here, right? Utilized by this conformation is this is 7.5. And in the cyclohexanone, right? In the cyclohexanone, the methyl substitution, so it utilizes the 6.6 potential energy, free energy or the potential. You say it is potential energy here. And upon addition of means increase of one more carbon like ethane, right? The change of that energy is in the cyclohexane it is 8.1 and here is 8.5 4.5 and here the tertiary group isopropyl group. When the isopropyl group is substituted, so here in the cyclohexanone is 1.6, it is 9. So in the normal, okay, so in the normal cyclohexanone, right? So it will more affected by this substitution here than your cyclohexanone. Okay, right. Now here, okay. So here in this particular, right? So in this particular two substitute alkyl substituted cyclohexanone, okay. So where the substitution of the bulky group in the equatorial position, right? Substitution of the bulky group in the equatorial position, which results in the destabilizing of the cyclohexanone conformation. That is called the 2-alkyl ketone effect here. Right? If it is in the okay, if it is in the axial position, okay, if it is in the axial position here, so you see that this much right? So this much what is that? So the space is there. So the carbonyl group and the alkyl group spatially separated, right? So there is no steric repulsion here. That's why this will be somewhat stable and this is the less stable here. The equatorial conformation is the less stable and the axial conformation is the more stable. In the chair conformation, right? In the chair conformation. But in the board conformation, that is the another aspect here. Right? Okay. And here you take that tertiary butyl group here, right? How it will be impact on the carbonyl function, right? Now you see that when the tertiary butyl group is substituted at second position here, right? So here, as we discussed here, when the methyl, the other any bulky group is substituted at C2 position, okay, so it results in the destabilization of this particular ketone functional. Okay, so you see, right? So this tertiary butyl group, this tertiary butyl group here, this is a bulky group, isn't it? It is a bulky group here. So it suffers from the steric strain here because there are three methyl groups are there, and here all the hydrogens. So this here you see the steric repulsion between the methyl group and this tertiary butyl and carbonyl group here, right? In the chair conformation, right? In the chair conformation, you see this effect here. So upon flipping of the molar bond here, when you convert this chair conformation into boat conformation, right? Here also, okay. So in the boat conformation also, you can observe, right? So you can observe that repulsion here, right? In that twist boat also, right? So in the twist boat, where right? So here in this when it is in the equatorial, when it is in the equatorial direction here, equatorial direction. So in the here also you see some steric repulsion here. Okay. And in the axial, sorry, in the equatorial, that in the twist boat form, right? So in the twist boat form, so so in the twist boat here, the boat form is here. You can see the right where the fractionally nearer here, the carbonyl group and tertiary butyl group, they are fractionally nearer. So that's why it suffers from the steric repulsion here, and in the twist boat form also, right? So where this carbonyl group and the tertiary butyl group here. In the twist boat also you have some effect, right? The steric effect on that one. That's why the equatorial conformer is a right destabilized, other less stable in all conformers like chair conformation, boat conformation, twist boat conformation. The equatorial conformer is a less stable here. And in the axial direction, in the axial conformation, right? So when the tertiary butyl group is in the axial orientation, okay. So here this tertiary butyl group is here also you can see the right. So the repulsion or the interaction with this particular flagpole hydrogens here, right? So in the board conformation, so here right. So you see this particular tertiary butyl group, it will have the interaction with these hydrogens here, C3, C2, C3 interactions here. Okay. And in the twist boat form, right? So this bond is, right? So here above the plane here. It is above the plane, right? Above the plane here. And this CO group is on the plane here, right? It is on the plane. This is above the plane. So both are in the opposite direction, right? These two groups are in the opposite direction here. So opposite direction. So you cannot observe any interactions or the repulsions here, right? That's why this is the stablest conformation here. The axial conformation of the fist boat is a stablest conformation. And in the tertiary butyl cyclohexanone also, right? In the di substitute, okay, tertiary butyl cyclohexane also, you can see this, observe the same criteria and the same phenomena here. Okay, here the in both chair conformation, right? Chair conformation as well as your board conformation. Okay, so both will be less stable here, and the twist board conformation, right? So in the twist board conformation, where this particular, right? So equatorial conformer, sorry. Okay, in the twist board conformation, where your this particular axial conformer is the most stable, right? Because here in the axial conformer, where these two are, okay, it is opposite direction to this carbonyl here. But in the equatorial conformer, right? In the equatorial, so you see this, right? The what is it? They are fractionally nearer. That's why the some effect will be there. Now coming to this C-alkyl ketone effect. So 3-alkyl ketone effect. So in the 3-alkyl ketone effect, here where the substitution of the alkyl group to third position, right? So in this particular 3-alkyl substitution, where the axial, right? The axial conformer, okay, the axial conformer is a less stable because it is having, right? So it is having one synaxial interaction here. Okay, synaxial interaction here. But in this particular equatorial conformer, right? So the synaxial right interaction is neglected or the removed here. That's why this is the more stable. Okay, and here you see the synaxial interaction here, right? And here also you see this same. Okay, next catalytic reduction reaction. Right? So in the reduction reactions of the bridged compounds here. Okay, the bridged compounds. So in the bridged compounds, how that particular uh, reduction, catalytic reduction reactions takes place, and what will be the orientation, right? The orientation of carbonyl group, how it will be impact on the reduction reaction here. You see in this 2-norbornanone, right? Norbornanone here. In this particular norbornanone, the catalytic reduction in the place of you take any hydrogenation reaction like hydrogen in the nickel, right? Or any lithium aluminum hydride or any reducing agents are used here. Okay, here the hydrogen plus catalyst, like you take any nickel or platinum and palladium. Okay, that will be used here. Now, yeah, the attack is there are two directions. The attack will be only two direction. It may be attack from the right? So what is it? Exo attack here, right? Endo attack and exo attack here. So yeah, exo means okay. So endo attack and exo attack. Exo is from the front side attack here. Okay, on the top side. So top phase attack here. This is the exo attack of this hydrogens. Okay, the addition of the hydrogen here from the top side here. Okay, and you see here when it is from the top side, right? So the formed alcohol is a right endo here. When the exo attack is takes place, the product is endo product here. If it attack from the right here, what is that? Endo attack here, bottom phase, right? When it is from the top phase here, top phase is exo and bottom phase is a endo here. when the bottom phase attack is takes place, then the formed alcohol is right. Yeah. Okay. So here, so this is exo alcohol and this is endo alcohol, right? Endo alcohol. So now you see when the this endo alcohol is okay, endo alcohol is resulting from the exo attack or the exo addition here, and exo alcohol is resulting from the endo attack of the hydrogen. So when the OH group is bulky group here, right? The OH group is a bulky group, and here the bridged carbon is there. The bridged carbon is there in the norbornene. In the norbornene, there are bridged carbon is there. So these two are okay. So the alcohol and this bridged carbon is repulsive each other here. Both will be repulsive each other. That's why the steric repulsion leads to leads to decrease of the product here. That's why if the this exo attack is preferred and the endo product, right? The exo attack results in the endo product. Here you see more than 80% of results, more than 80% of product is obtained, yield, more than 80% yield will be obtained. Okay? That's why the right, so that particular exo attack is preferred and endo attack is disfavored here. Now here in the when that particular right, so the bridged carbon is having the substitution here. Bridged carbon is having the substitution here. This center is blocked here, right? It is blocked. That is a camphor here, right? So the camphor, it is a alkaloid. Sorry, it is a terpenide here. Camphor is a terpenide. Okay. So in this camphor, you see the carbonyl group is okay. So here at second position, 1, 2, 3, 4, 5, 6. Okay, at sixth position, you see the methyl group here. C, right? At C6 carrying the methyl group here. Means this right? So this center is blocked here. So in this condition, which attack is preferred? Okay, so the addition takes place from which side? Either top side or the bottom side here, right? So in this case, okay, so in this case, if means here, if hydrogen, right, exo attack here, exo attack, right? So exo attack is disfavored because there is a methyl group here, right? So methyl group. So the hydrogen will not be approach this carbonyl group here because the methyl group will be rejects that attack of that hydrogens here. That's why the addition will not be possible from the exo attack here, right? So when the hydrogens are coming from here, so this methyl will be prevent to attack hydrogen here. That's why this exo attack is right. Exo is disfavored. That's why the endo attack. Endo means bottom side. So it is favored, right? When the hydrogen is attacked from the top, bottom side and resulting, right? The resulting product is a exo alcohol. The resulting product is a exo alcohol here. And yeah, and here also you see, right? Here in the tertiary butyl cyclohexone. No, Right? So generally, here you see, right, the attack is from the bottom side here. It won't come from the top side because the bottom side is sterically free. So the exoalcohol, right? Here is a exoalcohol formation is axial, the axial here because it is cyclo chain conformation. So here the axial alcohol, right? The equatorial attack is preferred or the favored, and the axial alcohol is formed. Right? So this kind of phenomena is called the steric approach control. Right? Steric SAC. Very, very important. SAC means steric approach control. So what is steric approach control here? When the product formation, okay. So when the product formation is decided by, right, the steric factor here. Okay. So here generally, in general, okay, in the previous class we discussed here with, okay, here I will show you. Okay, right. So here you see the alcohol, right? The endo alcohol formation is more than 80% here. Okay. Exo is a preferred here because there is no steric groups here. But in this case, right? In this case, here also same thing. Right. So here you see this is the exo alcohol. Right. So it suffers from this steric repulsion, right? Here the CH3 methyl and hydroxy group here. Okay. So here you see that, but the addition will not be takes place here because the hydrogen will not be approach this carbonyl group here. So the addition not possible here. Okay, that's why the product formation is exo alcohol. Right. So this, but generally, right. So this is less stable. Okay, so it is less stable here, and okay, it is less stable and major product. Product is a major and stability is a less here. Right here, the product formation is takes place. Okay, the product formation is decided by the steric factor. That is called the steric approach control. Right? SAC. SAC. Steric approach control. And one more thing is a PDC. Product development control. Right? So the previous one, this is the PDC here. Okay? This is your PDC. Product development control. So the product means the product formation is depending on the stability of the product here, right? The stability factor here the okay, the where the formation of the product is stable, right? So this is the PDC, and other one is the SAC, steric approach control, right? So here you cholesterol here. So here also you see this with okay, the axial attack is preferred because when this right, so here when this right, hydrogens are this is a less hindered here, right? And the product formation is it is equatorial reduction here, also reduction only. The equatorial alcohol is more, right? And it won't approach from the uh, top side, because here hydrogens are there, so it will suffers from this steric repulsion. Yeah, here you see the PDC. One more example under this PDC is a product development control. Okay, so this is equatorial, right? So here you see, for example, right? So if here the reagent is, right, lithium aluminum hydride, when the reagent is attacked from the top side here, you will get the equatorial alcohol. So generally equatorial, right? This equatorial. So this is stable, more stable, right? 1,3. Okay. So in the 1,3, di-equatorial or the diaxial is a trans here. Okay. So in the 1,2, axial equatorial is a cis. And in the 1,2, axial diaxial or diaxial or di-equatorial is a trans. Right. Okay. So like that, here you see, when this particular attack is from this top side, right? Equatorial axial attack, then equatorial alcohol is formed. So both the groups are in the equatorial direction, means a trans direction, right? Trans direction. So the product formed is a mode. Okay. And if it is attacked from bottom side here, so the alcohol formation is takes place here, right? So axial alcohol here, right? Axial alcohol is, so here, if the bottom attack. Okay. So this is equatorial, this is axial. So axial equatorial is a cis, the 1,3, right? So generally cis is a less stable here. That's why when it is attacked from the top side, the alcohol will be the equatorial. Then equatorial, di-equatorial is a trans one. That's why here the product formation is controlled by the stability here. That's why it is called PDC, product development control. So in the SCSE, okay, in the SCSE, so we won't see the stability of the product. We won't consider the stability of the product here. In the PDC, we'll see the stability of the product. Okay, and in the SCSE, the approach. Okay, we see the approach here, where sterically free approach. So the which side is facilitates for the attack here. Okay, right. This is a two terminology important here. Okay. Now here also all these the various compounds formation and the substitution of the various groups and the impact on the, right, equatorial alcohol itself. So you see, go through this table. Right. So now here the bicyclic compounds, the conformations of the bicyclic compounds here. Right? Here the cyclooctane and in the bicyclic compound. Yeah. Right. So in the piperidine, heterocyclic compounds. Right. So the conformations of the heterocyclic compounds. Right. So in the heterocyclic compounds, generally the heteroatoms, which are the incorporated by heteroatoms like nitrogen, oxygen, sulfur. Okay. If the cyclic compounds are incorporated with the nitrogen, oxygen, sulfur, so then it is called the heterocyclic compound. And in these heterocyclic compounds, generally they are carrying the lone pair electrons here, right? The unhybridized orbital. Okay, send us that empty orbit, that unhybridized orbital, right? That also impact on the conformation here, the stability of the product. Okay, so you see in this particular piperidine, right? In the piperidine, this one. Right? So here the hydrogen is there, here the lone pair. Right? So when it is converted into chair conformation, right? So in the piperidine, you see when this hydrogen is in the equatorial, right? So upon pyramidal inversion, PI means the pyramidal inversion, because the in ammonia, right? So it is ammonia derivative generally. So the ammonia, it is okay, pyramidal shape, right? Pyramidal shape here. It's pyramidal shape, right? Right. So when it okay, right. So upon the pyramidal inversion, where this equatorial hydrogen, it is converting to axial hydrogen here, and further, right? Upon further conversion, so it is going to where this axial hydrogen convert to equatorial. Again, further it is going to axial. So like the sequential changing of the position of the hydrogen, orientation of the hydrogen, right? And among these, so generally here, this particular, right? So equatorial, okay, the equatorial hydrogen is the most stable. Okay. So here the N equatorial hydrogen, this conformation is the most stable, right? And hydrogen, when it is in the axial orientation, so it is less stable. You see, right? Okay, so this is more stable. Okay, this is less stable because you see in this particular here the hydrogen is there, right? So it will be suffers from the steric strain. And in the when the hydrogen is substituted with this methyl group, so N-methyl piperidine. So the conformation is important here, right? Here this piperidine, right? So in the examination, they will ask that uh, draw the conformation of piperidine here, or draw the conformation of N-methyl piperidine. So like that. So then you have to simply you draw this conformation here, this conformation, and you give the and predict the stable conformation. Give the explanation. Right? In the examination, they will ask like this: draw the conformation of piperidine and predict the predict the stable conformation of the piperidine. Right? In that case, you have to draw this conformation and you give the stable conformer here. Okay, so the stable conformer is a N. This is a stable conformer. Right? When the hydrogen is in the equatorial, this is the stable conformer. Now, when the hydrogen is replaced with this methyl group here, right? So N-methyl piperidine. So here also you can see the same scenario of your particular piperidine here, right? So in this case also, right, in the N-methyl, piperidine also, where this N-methyl equatorial, right? When the methyl is in the equatorial, this is the stablest conformers. This is the stable conformer here. Like your piperidine, this is a stable conformer, right? So why it is stable? So generally, all the destability factors are absent here, right? All the destability factors like steric repulsions here, okay, and angle strain, all this, gauge interactions. So everything is absent in this. And in the axial, right? So in the axial, you have the right steric interactions here, steric repulsions, right? So where this, right? So this will be repulsive each other. And when the dye substitution is there, right? So in the dye substitution is there, in that case, which is the more stable, which is the less stable. So generally in the 1,3 dye substitution, right? So in the 1,3 dye substitution, so here the diaxial, right? Diaxial is the most stable. So the stability order is diequatorial most stable, sir. Diequatorial, then axial equatorial, then axial. This is the stability order, right? This is the stability order of the various conformers here. When the two groups are oriented equatorially, that is more stable. Then axial equatorial here, then diaxial. This is the stability order of 1,3 conformers here. Right? So in this particular dimethyl pyridine also, you see where this equatorial is more stable here. Right? Then upon the ring inversion, right? Ring inversion, so where it is converting into diaxial conformer here. Okay. So here, but here the diaxial conformer, it is suffering from this repulsions here, you see. Okay. So that is less stable here. Due to this, this is a less stable here. And in the further, right, upon the ring inversion, further it is going to produce the axial equatorial conformer. Right? So by holding one carbon, just you flip the one bond inside or the outside here, then you will get this particular trans conformer, axial equatorial. So in that case, this is also less stable here, because here you see this group is right. So it is having some steric repulsion. Right? And okay, now the very important, the conformations of bicyclic compounds, decalins, right? Cyclic decalins. Okay. So here the cyclic decalins, the explanation of this cyclic decalin can be done by the Newman projection. It is better way to explain the stability of decalins here. Okay, so first we'll see the two conformers, right? The cyclic decalin, it will be decalin exists in the two conformations, right? Two conformation forms like diastereomers forms. That is cis decalin and trans decalin. Okay, cis decalin and trans decalin. And among these two, cis decalin and trans decalin, so which is more stable and which is less stable, you see here. So in the cis decalin, first we'll see the cis decalin. So this is also very, very important confirmation of, right? So this is, you can keep 10 stars here. Because, right? So means frequently asking this question here. Draw the conformations of decalins. So in that case, you draw the cis decalin and trans decalin. Okay? So in the decalin, generally it is the bicyclic nomenclature is bicyclo 4,4, right? So 4.4.0 decane here, right? So here, okay. So in the bicyclic nomenclature, generally we'll give like this here, right? Here 1, 2, 3, 4, and here also 1, 2, 3, 4. So the bicyclic compound. So you write first, you start with the bicyclo, and in the bracket here 4.4, and here in the bridge there is no carbon here. That's why we keep 0. If any carbon is there, right? For example, here right? In that case, right? So here this nomenclature is, here is a bicyclo 4.4.1 here, because the one bridge carbon is there, right? That's why like this we will give the nomenclature for this bicyclic compound. Okay, so here the bicyclo 4.4.0 4,4,0 decane. There are 10 carbons are there. Okay, yeah. So in this there are 2 rings are there. Okay, A and B, 2 rings here. Right. Now the orientation of this ring is either in the cis orientation, cis direction, or the trans direction. So in the cis decalin, first we'll see. So here, when this planar structure is converting into, right, the chair conformation. Okay, so this is the cis conformation, right? Because you see this right, this bond and this bond on the same direction, right? Here, this is also cis. It's also cis here, same direction. Okay, these are in the same direction, so cis here, right? Here you see this bond and this bond on the same. This is the equatorial, this is the axial here. So in 1,2 system, axial equatorial is a cis here, isn't it? So like that. So and upon doing the ring flipping, right? Ring flipping, we are getting these conformers here. Same thing we'll see. Okay, we'll convert this chair conformation into Newman projection, and we'll observe that here you see when it is converted into Newman projection, right? So here you see this gauge interactions, right? Yeah, this is gauge. Here also gauge. Here also gauge. Here also gauge, right? So there are 1, 2, 3. There are 3 gauge interactions are there, right? There are 3 gauge interactions here. A gauge butane interactions here. C4, C10, C9, C8 here, and C4, C10, C5, C6, C8, C9, C1, C2, C8, C9, C10, C4. So there are 4 gauge interactions. Okay. Right here, this is 1, and this is 2, this is 3, this is 4. There are 4 gauge interactions. Right? Here is 1, 2, here 3, and 4. There are 4 gauge interactions here. Okay. Yeah, just like this. That's why presence of these four gauge interactions. For each gauge interaction, it is 3.35 energy here, right? So there are for four. So how much you can calculate? And in this trans-decalin, right? In the trans-decalin, same thing you can have where these bonds are. Right? This hydrogen is for the differentiation. Generally, will shown with this right heavy line and dotted line. So this confirmation indicates the trans. Yes. Okay. And yeah, here also you see the in the trans-decalin when it is converted into Newman projection. Here also you see the same thing, right? Here the gauge interactions here. Okay. So here also you have the gauge interactions, but you see that only the gauge interactions are there, but remaining all the right. So what is that? All the particular destabilizing factors are absent here, right? So here you see the right? And this cis, what is it? Dihydroquinones in all, right? So in all the remaining bicyclic compounds, the stability factor is explained on the basis of these, right? So steric factor and gauge interactions, all these things. And one more important is right propane, right? The propane here, propane, the conformation of propane. This is also important here. Okay? In the propane conformation, right? So when it is converted, right? So you can draw the conformation of propane here. Right? Okay. Yeah. And here you see that propane here, right? So N, it is what is it? It is bicyclic. It's also bicyclic compound here. And this propane, right? When it is converted into the chair conformation, right? So you have this conformation here, and upon the pyramidal inversion, right? So it is going to convert into this conformation. And now you see, right? So this methyl group is right in the tropane. The methyl group is equatorial here, and this methyl group is axial. Okay, this pair of lone pair electron is axial. Right here is the equatorial. Okay, so when it is in the equatorial direction, it is the major or the stable, right? And this is less stable. So less stable is more stable. Okay. So only the means the when the orientation of the methyl group is in the equatorial direction, so all the right the destabilizing factors are absent here, right? So here you see this the interaction of this methyl N methyl group with the hydrogen, so it causes for stability. Okay. So this is your confirmation analysis here. So I'm stopping here. So we'll start the next paper 5 minutes.